Hi everyone, we are the group 12. The below list is our group member. This is our midterm presentation. We will focus on the analysis of Pendulum. We will explain why the project name is GEPT later. And this is our today's outline. We'll start from our motivation and then talk about the introduction of our project. Next, we will explain our discovery and understanding about the pendulum and do some analysis to them. And then we will show our simulation by Python in brief. Last, we will briefly talk about the plan of the project realization. Okay, first I'm going to talk about the motivation of our project. One day, we went to the sport field and run there. We found that running is boring sometimes. There wasn't anything that is funny. However, there was a girl pass us, and we are attracted by her elegant, beautiful, and amazing swinging ponytail. Then we come up with the ODE project ideas. The motion of ponytail is similar to the pendulum, so we want to do the project about pendulum and discuss further analysis of different kind of pendulum. This is why the title named GEPT, Girl's Elegant Ponytail. And then let's start our introduction.
Let's talk about what is pendulum. A pendulum is a weight suspended from a pivot so that it can swing freely. When a pendulum is displaced sideways from its resting and released, gravity causes it to swing back and forth. A simple pendulum has a small diameter ball and a string that has a very small mass but is strong enough. We can know that the period of a simple gravity pendulum depends on its length, the gravity, and a small angle theta that is called the amplitude. We can show that the restoring force is directly proportional to the displacement. Then we have a simple harmonic oscillator. And the period of a pendulum for small amplitudes is the following, like this. The true period of an ideal simple gravity pendulum can be written in several different forms when the amplitude is more larger than 1, and the form one of that can be written in infinite series. And a double pendulum is a pendulum with another pendulum attached to its end, showing like the figure. And several variants of the double pendulum may be considered, such as the length and the mass of the rods or the ball. And in our project, we will only consider the mass of the ball and ignore the mass of the rods.
Then let's talk about the understanding and discovery of our project. Next page. If we can analyze the period of each pendulum, we can use it as a measurement of time. If we simplify a double pendulum as a system of two mass points and two strings of no weight, which is shown on the right side, we can analyze the period of the system by calculating the motion of two mass points with two strings that constrain their trajectory. So we consider analyzing two mass points M1 and M2. However, let's move on to the next page. Before calculating the period of the system, let's first take a look at the chaos theory. Chaos theory is a scientific theory that focuses on underlying patterns and deterministic laws highly sensitive to initial conditions in dynamic systems that were thought to have completely random state of disorder and irregularities. For example, a celestial system with multiple objects, weather systems, and subject we are analyzing, a double pendulum. A chaos system has the following features. First, it is sensitive to initial conditions. An example of three double pendulums with small difference in initial conditions are shown on the right side. It's obvious that the motion differs a lot between different double pendulums. Second, it is non-periodicity. This feature implies that our goal to find a period of a double pendulum is generally not possible. However, we might be able to find a periodic solution in a particular circumstance. Next page. Then let's start analyzing our system. To simplify the equation, we assume two mass points have the same mass. Next, we introduce Lagrangian mechanics to our system. By the basic assumption of the Lagrangian mechanics, we have to calculate the Lagrangian of the system, which is defined by kinetic energy minus potential energy. So we will yield the following equation here. The total kinetic energy is the sum of translational and rotational kinetic energy. The translational kinetic energy is calculated by its mass and velocity. And since we view the pendulum as a mass point, the torque is zero. Therefore, the rotational kinetic energy of our system is zero. So we don't have to consider it. But in case we still put it in our equations. And the potential energy of the system is the mass times the gravitational constant and the height of the mass point. Then we can yield a function of time to the positions of the mass point by solving these Lagrange equations below here.
Okay, so by the above derivation, we can find the explicit formula for the time evolution of a system given its current state. The below equation is a solution by the derivation. However, we can directly do the integration to obtain the formulas for theta 1 and theta 2 as a function of the time, but it's still possible to perform the integration numerically by a Runge-Kutta method. To sum up, we found that the current version of problem is too difficult to tackle. In addition, the above Lagrangian method is too recondite to have deeper insight. Thus, we are trying to simplify our analysis to make the project more realistic and find out more about our project. But the question is, how can we simplify the problem? What if we consider the double pendulum with small angle oscillations?
We will start off with a diagram of a double pendulum. Suppose 2 point masses are each m, and the two massless strings are length h. Let x1 and y1 be the x and y position of the upper ball, and x2, y2 be the x and y position of the lower ball. And we will set the origin of the system to be the point here. And T1 and T2 is the tension on the string, upper string and the lower string. Upper string is T1 and lower string is T2. Then we can calculate the x1, y1, x2, y2 position by some trigonometry. And we want to analyze the motion of the double pendulum under small angle oscillations. In this case, we will know that sin theta is approximate to theta, and cosine theta is approximate to 1. So we can write x1, y1, x2, y2 in this form. Note that y1 and y2 are also constant during small amplitude, so we can ignore the y component of acceleration. And with small amplitude, T1 will be equal to approximate to 2 mg. M is the mass and g is the gravity, 9.8, and T2 is approximate to mg. By Newton's laws, we will have these two following equations. And solving for x1, we will have this, and solving for x2 will be similar. And if we let omega 0 to be this, and substitute this thing to omega square, then we can rewrite the equation in this form. and write it with matrix expression will be simpler for us to solve it. And to solve this differential equation, we assume that the solution will have the form c times cosine omega t plus delta. So we can write x1 of t and x2 of t in these two equations, and also the second derivative of x1 and x2. Then we plug this equation into the matrix. We can write down this. To solve the equation, we can solve omega by taking the determinant. This will be a second equation with the it's simple to solve. And with omega, we will have the period t to know the period of the double pendulum.
Now, it's my turn to introduce the use of the Python to simulate a double pendulum. First of all, we need SIPY ODEINT to solve the double pendulum formula, and use PLT to materialize our simulation result. There are tools such as function animation and INT Procress to help with coding. Next is the initialize part. I set the L and M variable to determine the width ratio of the rod to the mass point of our model. Then we can establish two formulas based on the result derived from understanding and discovery. Like that. In order to do mathematical calculations, we can organize the material power formula into V and T. In the previous block, we successfully sorted out the Lagrange equation. So we can solve the differential equation solved SIPY ODEINT. Among them, the initial condition we need to give is the speed and the position of the two centroids in our simulation system. Like that. Because the extreme of the simulation parameters will affect the error, we will warn about excessive energy drift. Finally, we enter the simulation link. We first establish the function for each time t, put t into the previous solved equation, and put output into pyplot and save it under the path of dash frames. And we set the total simulation time and the number of the simulation per second to simulate, one by loop, and the output of each of our time by embedding Bash into Jupyter Notebook, using FFmpeg to combine photos into GIF files. After the simulation of previous code, we can see the result of the simulation. This picture is the result of a one-dimension simulation with two mass points, blue and red one, being projected at an unstructured angle. The picture in the upper right corner is vibration trajectory of 2 points on a one-dimension axis according to time. The two photos in the lower right corner are simulation of small angles, and the angles of the two nodes are plotted to get a variregulation graph, and the path difference can be affected by the angle and the speed of initial condition. If you want to see more details of the implementation, you can check it out on our GitHub.
Okay, so I will talk about our plan. And since we are using a double pendulum as a clock, we need a real double pendulum to examine our experiment and to evaluate how well it performs. So our physical realization of our clock will using bearing and some 3D printing gadgets. And now let's talk about what bearing and why we need to use it. Bearing is a machine element that can reduce friction and vibration between moving parts. I think there are some toys using bearing. I think the most famous one is this finger spinner. A bearing has an inner ring and outer ring. The outer ring is usually held stationary, while the inner ring has extremely tight tolerance and is hung to be very smooth surface. And we will use it so that our pendulum can swing smoothly and frictionlessly. Let's see what 3D printing gadget we will print and use. So there are 2 rods with 2 holes, and those holes are preserved. There are 2 holes has space preserved for bearing, and there are 1 rod with 1 hole and a cylinder which has preserved space so that we can adjust balance. And there are 2 sticks. Okay. We will use rods with 2 holes as upper pendulum and rods with 1 hole as lower pendulum to simulate double pendulum. Now let's talk about how we assemble the gadget and bearing as a single pendulum. We first put bearing into rods with holes and fix the bearing using glue. We insert 3D printing sticks into the inner ring of the bearing. And now we have a stick in the inner side of the bearing and rods in the outer side of the bearing. When we hold the stick, it won't affect the swing of the rod. Now let's talk about how we assemble the gadget and bearing as a double pendulum. So remember the single pendulum in the previous slide. So to make the double pendulum, we combine rods with 2 holes with single pendulum. So we will have a double pendulum like this.
Next, let's talk about some possible future works. First, we might consider some different kinds of pendulums and their performance on time measuring. And second, we might consider the errors of our analysis. Since the previous models didn't consider some real variables like fractions and the weight of the string, we might take these factors into consideration and conduct experiment on real ponytails and breed, if possible. If we can find someone to conduct our experiment, we might do it. Next, we will develop an application that can emulate the pendulum with user-friendly UI. And finally, we want to design a method that can evaluate the cuteness of a ponytail. That's all of our presentation. Thanks for your attention.